Okay. Hello, everyone. Thank you so much for coming, and also thank you for the opportunity to be here, of course. Today, I'm going to present my work about multi-scale vortex detection for a vortex ring state characterization. So during this conference, we have been discussing about the definition of the vortex and also about different vortex identification methods. And today I would like to discuss how we use the different methods in the context of a rotorcraft flow. So in particular, I'm going to focus on two different operation conditions because we have the rotor wake structure, and if we modify the operating condition of the rotor, of the helicopter rotors, the wake the structure change. So that's the reason, because here I'm focused on a ground effect and also in a vortex ring state, because both conditions are can be dangerous. Both can be a little bit dangerous for the rotor. And then I will, in the second part of the presentation, I'm going to show you some experimental results obtained from particle image velocimetry, both in 2D and also in 3D for vortex ring state and also for the ground effect. Okay, this doesn't work. Okay, so rotorcraft, I know that maybe most of you know, undergo a complex aerodynamics effect is because there are many complex aerodynamic interactions that we can have here, because there are many, we can find sharp gains, velocity, and also pressure near the blades. So, and rotors generate lifts by rotating the blades, and the shooting of the vortices is an inherent part of the procedure. So here each blade shoot a deep vortices, and that then roll up in a helical wake structure. So the vortices close to the propeller are in a coherent structure, but then they start to break down in far wake. Okay, so but now the question is, why do we want to study the vortex structure of this kind of wake? So the thing is. So the thing is, we want to focus on the rotor wakes because we are interested to know what is happening in the new concept of rotor configuration. So in particular, we focus on multi-rotor and also in eVTOL. So this picture, okay, this doesn't work. Okay, this prototype, large multi-rotor, is developed by my colleagues in Delft, and we used to perform many experiments in Delft. And then I show you also the Joby eVTOL because we are inspired by this kind of vehicle. So the thing is, if we want to work with this kind of vehicle, we need to understand what is happening with the rotor wake. So here I include a picture where we can see how the rotor wake can be modified if we introduce an additional propeller, or maybe we consider the interaction with the structure itself. So here I'm showing you the vorticity of the rotor. This is in a plane, here in a specific plane, and here we can see how the vorticity, how the vortices are opposite direction on each side. So we use this condition as a reference, and then we try to see how this trajectory change if we consider a different operating condition, like a ground effect or a vortex ring state. Okay, let's start with the vortex ring state. The vortex ring state occurs when the rotor descends fast enough that the deep vortices are no longer convected away. So here I include a video where we can see a real experiment of a helicopter. So in this case, the rotor starts re-ingest his own wake, and here we can see the formation of this vortex ring around the propeller. So this is because we have the tip vortices, and then when the rotor starts descending, we have this velocity. When both velocities are comparable to each other, like the ratio between both velocities is close to 1, we have this big vortex around the propeller. The formation of this vortex causes a loss in thrust, and maybe we can, there are many options that, for example, the helicopter can crash. So in this figure, for example, we see the formation of this vortex ring, and also we can see how the pilot is trying to increase the descent velocity to move the vortices upstream to recover the helicopter. Is one of the techniques. So in our work, we are interested to study this phenomena because this is very dangerous for this kind of vehicles. And the innovation for us, the motivation is based on this, but we want to know what is happening if we include the inclined conditions. Because if we include the inclined condition, these vortices are not symmetric anymore. Then the next question, it could be what happens if we place a solid boundary below the rotor? Because here we have in the previous case, we have the flow interaction with another flow. But here we have the flow interaction with a solid boundary. So here, when the propeller approaches to the surfaces, here, when the propeller approaches to the surface, we can see how the tip vortices move downwards, and then they are forced to move outwards because we have the lateral expansion because of the wall here. Also, we encounter a stagnation region because the flow decelerates in this area and then start accelerate again. So in this case, we have a reduction in the induced velocity, which produces an increase in thrust. That's the reason because here we want also to study this phenomenon, because in ground effect, we can experience a 20% of the increase in thrust, and we need to know in advance what happened for different kind of rotor configuration, because this is for the typical single rotor, but what happens if we want to study a coaxial configuration. These configurations are very typical in eVTOL vehicles. So that's the motivation, and now I'm going to, okay. So before going for the experimental results, these are the objective for our work. So the idea is try to characterize the spatial organization of the vertical structure in different operating conditions that could be dangerous for the rotor, like a ground effect or a vortex ring state, because in both cases we have for an increase in thrust or decrease in thrust, which is this condition of dangerous, and we need to understand what is happening with the vertical structure point of view. Then we need to describe how the external conditions modify the symmetry of the vehicle, like for example with oblique descent, also the coherence of the vertical structure and the topology. And finally, we want to identify this structure both in 2D and also in 3D to be able to reconstruct the vortex structure. Okay, let's start with the 2D planar PAV. So here, I'm showing you the experimental setup that we built to analyze the ground effect. First, we start with a single rotor. Here we have the rotor, and this is the distance from the ground. And then we introduce an additional propeller. So the bottom rotor and the single rotor are in the same position in the distance set from the ground. And then I introduce an additional propeller. Both are contra-rotating, and they share the same axis of rotation. So the distance d also we change it during the experiment to know what is happening if we modify both set and also t. So, and this is our experimental setup. Here you can see this arrow. If we move, we can move with this being the propeller in this direction and also this direction to modify the different conditions. So here we use 2 cameras and also a laser to illuminate the field of view. Which we select a plane to detect the tip vortices and also to see how is the interaction between both propeller and also the interaction with the ground plane. Okay, so here we use the instantaneous vorticity distribution to show the ground effect, to characterize the ground effect, because in this way we can see how the flow interacts with the ground through the boundary layers and also with the vortex wall interaction. So here I include some videos, I think. Okay. In both cases, these results are only for a single propeller for two different distances. This is for 0.5 r. This is r is the radius of the propeller, and this is for 1 r. R is a bigger distance from the ground. And here in the first video, we can see how the vortex convect downward, and then when they interact with the ground, they start dissipating along the boundary. Then, if we increase the distance from the ground, the coherence remains in the wake, but then we can start see the diffusion here. Also, the boundary layer in this case is thinner, but it has a higher near wave velocity and a stronger shear due to the confine of the wall jet flow, because here we have the wall jet flow. Here in this case, when we increase the distance, the boundary layer is thicker, has the velocity gradients we can see in this case. So this is what I mentioned before, because here we had the flow is decelerated, and then here the flow is accelerated. But if we increase the distance, the velocity close to the wall are lower. But now the question is, what's happening if we introduce an additional propeller? So here we have an additional effect. It's called blade vortex interaction, and this interaction appears. This interaction appears when the tip vortices of the top rotor interact with the lower rotor. So this interaction causes a large fluctuation in the thrust, noise, vibration. So that's the reason, because we need to understand what is happening here and how affect this vortex. Also, if we increase the distance between these two propellers, we can see how this vortex moves inward. Yeah, the behavior is similar. Also here, because of the blade vortex interaction, we can see some small scale vortex because of that, and also how increase the unsteadiness of the flow. Then, if we increase the distance from the ground, in all the cases, the bottom rotor is the same as the single, because we want to quantify how change the flow if we introduce an additional propeller. So in this case, we have a similar pattern, but we also can see the blade vortex, the vortex interaction between these two propellers, and also the dissipation in this area. And also in this case, we have a small scale vortex because of this interaction. Okay, next I'm going to switch to the vortex running state in 2D and also in 3D. I'm going to start in 2D. So in this case, we have the propeller. We have the propeller in this position. I'm going to show this area, and also we consider a constant velocity of the propeller and also a constant distance velocity. So first, I'm showing you a snapshot from our instantaneous measurements. This is the vorticity. Also, we use the vorticity in this case, and here we can see how the vortex trajectory are bent and are distorted because the incoming flow. The incoming flow is from the bottom, and then the flow from the propeller go against to the descent velocity. That's the reason, because we can see this trajectory here, and here leading to a large scale structure, because here this is the region where the large scale structure is going to form. I can show you later. Then, if we want to explore more snapshots, so here I include a sequence of different snapshots. This is 1, 2, 3, and 4. We can see how the vorticity changes significantly between the different cases, highlighting that the unsteadiness is very high. Actually, the strong non-stationary is a characteristic feature of the VRS. And this behavior occurs because the vortex frame is a three-dimensional structure and moves continuously and is deforming. So that's the reason, because here in instantaneous measurement we cannot see exactly the same vortices that maybe we saw in the previous lead. So now, this one thing that I want to mention, this is for axial conditions where the propeller is descending vertically, but what's happening if we want to increase the inclination? So in that case, the flow is even more complex because the symmetry, because in that case we don't have the symmetry anymore. To quantify this phenomenon in 3D, the vortex frame state, we performed recently some experiment in Delft, and this is the experimental setup. So this is the experimental setup. In this case, we use a robotic arm just to position the propeller at different inclination relative to the tunnel. Also, we use different antennas. This system was developed from some college in Delft. And each antenna has different cameras, and also we have the LED to illuminate our measurement volume. The equipment is the cameras, the LED, we use a motor, also the robotic arm, and the operating condition that we use, it was between 0 and 14 meters per second. And also we tested different inclination of the propeller just to see how the vertical structure, the evolution of the vertical structure, and then see the topology for the different conditions. Okay, so this result, I'm going to show the time average result because it's an easy way to understand what is happening in vortex frame state with the inclination. In particular, I'm going to show the axial velocity, which we normalize with the hover-induced velocity. So this figure is the axial velocity when we have axial descent, when the inclination is 0. And for a specific descent velocity, in this case is for 7.5 meters, and all the cases has the same velocity. Otherwise, we cannot compare the axial condition with the inclination conditions. And here we can see clearly this is a toroidal structure below the rotor, and also we can detect the foci of both vortices in the vortex frame state. The position of these foci are around more or less 1 times the radius of the propeller. But what happens if we introduce for the same velocity, for the same rotation of the propeller, exactly condition inclination? So here, the inclination is 10 degrees. We keep the descent velocity, we keep the same velocity of the propeller. However, here we can see how this structure starts rotating in this way. And also here we can see how the foci move upstream, and also how the different saddle points S1 and S2 change his position relative to the axial conditions. But what's happening if we still increasing more the inclination? We have this topology. So in this case, the foci 2 is above the propeller. So if we compare this case with this case, we can see clearly the difference. This is asymmetric. Also, we have the saddle point very close to the propellers, and the structure here is different because it's dominated by the flow, by the descent velocity. So here we cannot see the induced velocity from the rotor because in this case it's dominated by the incoming flow. Then the last inclination that we tested during this experiment is 30 degrees. And here something's happened because here you can see that in this side we cannot detect this structure anymore, which means that the vortex breaks down and lose coherence in this area. So now, to understand a little bit more what is happening, we use the reconstruction in 3D. We use the Q continuum to visualize this vortex. So as you mentioned, during these days, we need to define a threshold for Q continuum. And in this case, to compare the different cases, the axial condition with the inclination, we choose to select the 85th% of the Q distribution. Because in this way, we can take the area when the rotation is dominated. And here, this is the side view, and this is the top view of the vortex. Here we can distinguish the black line is the rotor disc, and this vortex is related to the rotation of the propeller itself, and this vortex should be the vortex swing state. So in this case, we can see that the vortex is not in the rotor disc, which means that we are not in vortex swing state, because we are in vortex swing state when this big vortex is around the propeller, as I showed you in the previous video. But now the question is, if we remember the previous figure about the axial velocity, how is the vortex if we introduce the inclination in this way? So here we can see how this vortex changed totally his shape. Here the vortex starts entering in the rotor disc, while in this side is more or less in the same position. The Fauci move a little bit upstream, but we still keep the position of the Fauci. And here we can see also the shape of the vortex in top, and the size in general decrease a little bit if we compare with the axial conditions. Then for 20 degrees, we see that I want to remember that in all these cases we use the same descent velocity. So that means that we are in different states for the same velocity if we consider the inclination. That's the main point of this visualization. And here for 20 degrees, here we have the rotor disc here, also here we can see the deformation of the vortex, the asymmetry relative to the previous one, and also how the entire vortex is around the propeller itself. Which means that for this case, we are totally in vortex swing state. Here we are not in vortex swing state. And finally, this is for 30 degrees. If you remember in the previous slide when I showed the streamlines, we saw that in this side we didn't see the coherence of the vertical structure. So that means that the vortex in this area is totally open. The vortex breaks down in this side because the flow is dominated by the descent velocity. And now the question here, it could be, is the vortex swing state a real vortex or not? Because we use a Q criterion. Q criterion is a method to identify vortex, and we are able to identify the vortex here with our experimental result. But so in this case, can we consider this is a vortex? I don't think so. But we still can see it with this criterion. Okay, so finally, to conclude my presentation, these are the main points that I tried to discuss during my presentation. So rotor waves are built from concentrated vortex filaments who organize depending on the operating conditions. So that's the reason because we need to study the different conditions, or at least the condition that could be dangerous for some operations. Then we have we studied the ground effect in planar, which reveal a strong radial deflection of the vortices, and how they were modifying the induced velocity of the rotor, and also for coaxial configuration, we have the blade vortex interaction, which modify the localized vorticity intensification, which intensify the local vorticity, and also increase the unsteadiness of the flow. And finally, vortex real estate, the 2D measurements allow us to show the large unsteadiness in a specific plane. And then this, we need to consider the 3D measurements, where we are able to see the symmetric condition of our vertical structure. And also we see that for a very, very high inclination, we lose the vortex breakdown and lose his coherence. Yeah, which means that for us, a Cooper-Dino, it could be a very good method to identify at least the topology of our structure. But we need to think, is this is a real vortex or not? And this is all from my side. Thank you so much.